how much organic matter is present, including how many bacterial cells, and not just bacterial cells, but any microbes, how much of them are present, what's the pH that you're working with, and how much time are you willing to expose. So all of these contribute to the microbial death rate. Okay, so we have this method called the disc diffusion method, where these small discs are soaked in a disinfectant and placed on top of a lawn of bacteria. And then we look to see, does it kill, or really all we can see is it creating what we call a zone of inhibition, where bacteria are not, they're no longer growing in the presence of that. Also want to remind you that it's a diffusion, right? So the most concentrated of the chemical is on the disc, and then it's going to diffuse evenly in all directions, and so you get less and less and less of the chemical the farther you go away. So there very well could be chemical here in this place, but it's no longer strong enough to inhibit the growth of those bacterial cells. However, when you get to this region, it's now strong enough to inhibit the growth. So this zone of clearing or zone of inhibition around the disc is due to the chemical that's on the disc. Okay, so we would measure how in millimeters the diameter of this zone of inhibition, and then we would compare that to a chart or some manufacturer provided information, and it would tell you, based on the concentration that you put on the disc, if that zone of inhibition is considered large enough to be a good disinfectant or not. So these are not necessarily all the same concentration. So you cannot always just go off of appearance. Okay. So here we see the undiluted form of disinfectant and the diluted form. And the diluted form is a 1-to-10 dilution, and you can see that you have lots of colonies, and it doesn't seem to affect these colonies at all, right? They're growing. But with the undiluted, we see a large area of no growth, right? So the undiluted is strong enough to inhibit growth, and the diluted is not. Here we see different types of bacteria, right? Staphylococcus aureus, which is a gram-positive organism. We have E. coli, which is a gram-negative organism. And then we have Pseudomonas aeruginosa, which you know has that rapid efflux pump. So quats, the hexachlorophene, I know we haven't talked about these chemicals yet. We're going to O-phenolphenol, which is the active ingredient in Lysol, chlorine, which you would associate with bleach, right? And only the bleach was able to start to have some inhibition, and the others had no effect, likely due to that rapid efflux pump. Okay. E. coli, we see chlorine works very well. We see a little bit of zone on O-phenolphenol and quat, and no effect at all of the hexachlorophene. Remember, gram-negative have that outer membrane, and their cell walls a little different, because gram-positive cell walls have teichoic acid and gram-negative don't. And so all of these differences between gram-positive and gram-negative will impact how which chemicals work, etc. Okay, so this is a disc diffusion test. All right, so soap can physically remove germs from your hands or whatever you use it on, your dishes. It has a hydrophobic tail, which is going to interact with oil and attached. It's just physically removing them. Phenol, on the other hand, is actually attacking lipids, disrupting the plasma membrane. Phenol, if you recall from way back in chapter 1, we learned that the very first disinfectant applied to surgical tools, surgeons' hands, and even the surgical wounds by Lister was the phenol chemical, because he knew that it was effective disinfectant. But it actually can be quite irritating to the skin and have an unpleasant, strong odor. So we don't really use it anymore, even though that really is, it's still very significant because it changed the way medicine was practiced thereafter, greatly reduced the amount of infections and deaths in patients, so much better patient outcomes. It's also good because it can last long on surfaces, and so when we make a modification, we add another aromatic ring to it, and this is called O-phenyl phenol. This is the active ingredient in Lysol, and so this is what is more commonly used today rather than actual phenol, and so this is called a phenolinic because it's a derivative of phenol. Then we have bisphenols, the hexachlorophene, which the brand name is triclosan. This is still disrupting the plasma membrane, so it's the same mechanism, different chemical. Okay, so hexachlorophene and triclosan. Okay. Then we have a group called the halogens. And remember your periodic table from when you took chemistry, you have a row of halogens, and iodine and chlorine are on that, in that row. So iodine is safe for the skin, so it's an antiseptic. You will see quite often we'll see a tincture of iodine, which would be iodine in alcohol, that's used to clean the skin of a patient that's about to have a procedure, like a surgery. We'll see also iodophores, which is instead of mixing it in alcohol, you're mixing it in some other organic solvent. And these actually improve the effectiveness of iodine. How does iodine kill bacteria and microbes? It's going to attack protein synthesis and membranes. So it has two modes of action. There's a really great chart in your book. If you're using the current edition that I'm using, so I'm using the 13th edition. So if you're using the 13th edition with me, then you can look at page 199, and it has a nice summary of the different chemical agents and what their mechanism of action. How is it killing the microbes, or is it actually static and just inhibiting but not actually killing? So it tells you all that, and then it also shows you the application, like the preferred use. What's the common way that that chemical is used? So it's a really good chart. Make sure you look it over, and you probably want to make flashcards so that you can memorize these. If there's a chemical in your book that I don't discuss in lecture, then you don't need to know it. I'm only going to hold you accountable to what we have seen here in these slides, okay? All right, so chlorine, on the other hand, is not an antiseptic. You would not use this on the skin. I'm sure you already know that because you would never just put bleach on yourself, right? In fact, you should always wear gloves, probably even eye protection, and have a very good air ventilation when you clean with bleach. You should also dilute it, and you would look on the bottle to see how to do that because all the different bleach bottles are different concentrations. So, but typically you want a 1 to 10 dilution for bleach. Now, bleach can be actually a couple different formulas, but in the end, it's going to be a strong oxidizing agent. And we already saw that oxidizing agents kill through forming free radicals, right? Being super reactive and damaging molecules like DNA and other macromolecules as well. Okay. Alcohols we've talked about also from day one. It attacks lipids, right? So the cell membrane. It can also have some interactions with proteins and denature some proteins, but the main mode of action is typically that disruption of the membrane. So alcohols can be ethanol, which is better than isopropanol, is rubbing alcohol. Rubbing alcohol needs to be more concentrated and needs a little bit more contact time to achieve the same level of disinfection. I personally have done some tests to see this because I wasn't really finding literature on it. And so in my experience with, very limited amount of tests, but I found that isopropanol really is not equivalent to ethanol, even though it often is spoken as though it is. So in labs, when we want to disinfect countertops and things, we use ethanol. A minimum, the standard is 70%. So 70% is common for disinfection. And going too strong, going like 95% and above is not going to work. Alcohols will evaporate too quickly and they won't have time to actually interact with the cell and do any harm. So you need to actually add some water and dilute it. And you don't want to dilute it more than, I believe, 65. I have a chart here that shows you. So if you look at the concentration of ethanol, and NG stands for no growth, so that's what you want to obtain. You can go up to 95% pure ethanol, 5% water, and you will get no growth. But once you go above that, anything above that to up to 100% pure ethanol actually will not disinfect, right? So you get growth no matter the amount of seconds. Now, this is also kind of deceiving because it's saying up to 50 seconds, but as I said, like if you don't have some water, it cannot interact with the cell, and so you're not really getting actual contact for 50 seconds as you are with these other. If you dilute it more than 50%, it's not going to be effective. In fact, 50%, if you have a very short contact time, 10 to 20 seconds, that's also not enough, right? So if you want to be sure that you will actually kill, the standard is 70%. And you might be asking, well, why not? That seems wasteful. 60% looks good enough. Well, typically you get very quick evaporation, and so the exposure time is closer to 2 to 5 seconds. Think about when you put hand sanitizer on your hands. It's very fast, right? So we actually want to do 70% just to make sure that less than 10 seconds you'll still get some killing. So it's not really demonstrated in this graph here, but that's why. Okay, so the other nice thing I've told you about alcohols is that they evaporate, and so you don't get chemical residues like bleach. You have to be careful because it will actually leave a residue. And so in the lab, when we like our monthly deep clean, we would wipe everything down with a bleach solution, and then we would have to do a water rinse and then an ethanol rinse to make sure that we get all of that bleach residue off. But the bleach makes sure that you're killing anything that may have still been on that surface in between all of the regular ethanol wipes. Okay, so heavy metals don't always kill. They can denature proteins, for example, binding to or reacting with sulfur amino acids that have sulfur in those side chains. And we see silver nitrate can be a preventative treatment for gonorrhea way back when we were first starting to learn about microbes, this was a common practice. We have silver that can be used as a cream for burn patients to help prevent infection. So that's still practiced today to protect that. You know, you have that open wound, your skin barrier has been damaged, so we need to prevent infection that way. And then copper, if you've ever been around fish tanks, copper sulfate is added. It kind of tints the water like a green-blue color, and it helps slow down or prevent the growth of algae. Right, so heavy metals can be very effective, and depending on the concentration, you might see killing, or you might just see inhibition. And this picture here shows, silver and maybe some bronze and so some different metals. And if you move them, you can see that they did actually inhibit growth where there was direct contact, but they didn't diffuse, right? They're solid, so they didn't diffuse and cause a zone of clearance, but they do inhibit the growth where there is direct contact. Okay, so quaternary ammonium, so you see here is an ammonium ion, and then you can attach onto it another molecule, and so we call these quaternary ammonium. So these are positively charged ions, so cation, and they're considered detergents. You're going to see that there's an NH4 ammonium group, and you're also going to see a Cl. So see right here, Cl group. So these are really usually pretty good disinfectants, and they are targeting the plasma membrane. And we see a couple of different examples, brand names, Zifran and Cepacol. And you'll see in your book, they'll have like a little graph to show you their effectiveness as well, if you want to go ahead and take a look at that. So these are good, what we call surfactants or surface agents. This is why we consider them detergents typically. They can be good at kind of killing and disrupting plasma membranes, denaturing some proteins. They're very good at killing bacteria. And then we have the aldehydes, which are some of the most effective disinfectants. Unfortunately, formaldehyde is very dangerous. It's a carcinogen. So we have been using it less and less. It's mostly you only see it in preserved jars of specimens. We used to use it for even like preserving cadavers and animals that are being used in anatomy, but we don't even like to do that anymore. We don't want to expose anyone to the formaldehyde, so a lot of times other things are being used instead, but formaldehyde was really good. It would preserve things for a very long time. But it's very dangerous. So glutaraldehyde is actually commonly used for medical equipment. It doesn't have the same carcinic properties that formaldehyde has. Both of these have the same mode of action. They'll inactivate proteins by changing the bonds and cross-linking them. So rearranging the proteins. Okay, so peroxygens are oxidizing agents that form free radicals. This can be ozone, it can be hydrogen peroxide, or peracetic acid. Ozone is a gas, okay, and this is starting to become more popular as a disinfection method for water. It's very expensive. You have to have specialized infrastructure, and you have to have that gas, which is also expensive to produce. But it's nice because then you have zero chemical left in the water, and the water has been disinfected. So it's a good method. Hydrogen peroxide we've talked about a bit. We saw You can go back to chapter 5 and see how it doesn't stay as hydrogen peroxide, but it'll release a free radical that can be damaging. And so you'll get this oxidation damage, right? To DNA in particular is very susceptible to damage by free radicals, but it will do it to any molecule that it comes in contact with. Now, chemical food preservatives, we have to be, especially careful, and there's a limited amount of things that you can do, but we want to inhibit metabolism. We will not necessarily kill the organisms in the food, but just slow them down enough to preserve the food. There are things like sorbic acid, benzoic acid, calcium propionate. These are things that you might see on food labels towards the very bottom as a preservative. Salt is also still used as a preservative as well as a flavor enhancer. These organic acids that I mentioned are good at controlling molds and bacteria, and you also can find them in cosmetics, although cosmetics also tend to have a lot of the metals, and so you might not necessarily see these acids, or you'll see them in even smaller amounts. Nitrate, we already saw, I think silver nitrate, but nitrate itself can prevent endospore germination. And then we have certain antibiotics that have been cleared as safe to use. So you see niacin and neomycin. You would not see these ever prescribed for an infection, but you would see them used in the cheese industry. It's non-toxic and it doesn't have any taste, so that's pretty common. There can be residual amounts of this in your food, but like I said, it's not used for clinical purposes. Okay, so this is the graph I was actually thinking of earlier. So you can see soap is not really killing bacteria, although it can disrupt the plasma membrane. So over time, you can start to kill some, but you're going to be left with pretty much a very large amount of the bacteria after soap and water. If you use this brand name Zephyrin, which is Quaternary Ammonia, just by itself, it's actually not that effective. Okay, this is a dilution, a 1 to 1,000 dilution of this chemical. Better than soap, but still leaving a lot of surviving bacteria behind. But if you combine it with an alcohol, so you make a tincture, then you get a drastic increase in killing, right? So very few organisms left, especially once you get to 120 seconds. And then if you look at the tincture of iodine, just 1% of iodine and 70% ethanol is even more effective at killing bacteria. And these were all considered safe to use on the skin. So again, make sure you read that this is the amount of bacteria that survive after treatment. Okay. Here's a summary of the effectiveness of chemicals against endospores particularly, and mycobacteria. Remember, mycobacteria have that mycolic acid. They're a little more difficult to kill than regular bacteria, and tuberculosis is an example, right? The Clostridia are examples of endospore-forming bacteria. Okay, so mercury doesn't affect either of them. The phenolinics, very poor disinfection property for endospores, but pretty good for mycobacteria. Then we see the bisphenols and the quats actually don't impact either of these groups. Chlorine, a little bit, right? Iodine, very little effect on an endospore, but you don't really expect to find endospores on people's skin, and you could easily remove those from the surface of the skin, so that's why iodine is still a good disinfectant, antiseptic for pre-surgery. Mycobacteria, on the other hand, iodine can be pretty good at killing. And alcohols, not going to really affect endospores much, but they strong enough and the exposure is proper, they can actually be good at killing mycobacteria. And so I want you to not be confused. So when we do the acid-fast stain, we are using a particular strength of alcohol for a particular amount of time, and then the mycobacteria will be intact against the alcohol for that short amount of time. But if you increase the concentration or the amount of time, then you can actually get through the mycobacterium and kill them. Okay. Glutaraldehyde, as we saw, we don't use formaldehyde anymore, but we do use glutaraldehyde in hospitals. It's very good at killing mycobacteria, and it does a fair job of endospores, so it makes it a pretty good candidate. It's safe also. Chlorhexidine, we don't see affecting endospores at all, and a little bit mycobacteria. So these are the categories of what we talked about today. So good little summary to see. So you want to know, does it work against gram-positive? Does it work against gram-negative? Does it work against mycobacteria? Does it work against endospores? And then you want to look at viruses. Viruses can be enveloped or non-enveloped. So those are two more categories to look at, right? So prions, we haven't really talked about in class yet. These are just a protein, nothing else, just a protein, but it has an interesting property in that the next protein that it comes into contact with can be converted to be the same as it. So in a way, it's considered infectious because it will lead to more and more prions, more and more of itself. And this can be very dangerous in the body. So we'll talk about this when we get to our virus chapter. It's not a virus, it's just a protein, but we talk about it when we talk about the viruses, in that it's not a living organism, but it can be infectious. They're the most resistant infectious agent that we know of so far. Endospores would be next, and then the mycobacteria. Cysts of protozoa, which we also haven't really talked about protozoa. Remember, protozoa are eukaryotic organisms, single-celled eukaryotes, and they can be pretty resistant. A cyst is going to be more resistant than the vegetative growing form, but those are both still more resistant than gram-negative. Gram-negative tends to be more resistant than most of our fungi, and then we have viruses that are without envelopes, and then we have gram-positive, and then viruses with envelopes. So viruses with envelopes are very easily disrupted and deactivated. When they lose their envelopes, they lose their attachment ability. They lose their ability to go inside of the human cell and cause infection. So they're the easiest to get rid of. Okay, so memorize this order and try to think about the properties of these different infective agents and why they are more or less resistant. Okay, so that's the end.